Morning everyone, sorry I can't be there, a bit of a landslide issue that meant my trains are all cancelled. So I thought probably this is the best way to make sure that that you understand the concepts that I'd like to go through today without you just reading a book. Okay, so you can watch this, stop at any time, make some notes, and then we'll look at some examples. And then you can just refer back to this anytime that you want. So I really want to make sure that you are comfortable with, first of all, the latent heat idea, and also an idea about fusion and vaporization. And we're going to be looking at water. So if you remember latent heat, when we compare it to specific heat, latent heat is the amount of energy that's required to change the state of a substance without a change in temperature. Whereas specific heat capacity is the amount of energy required to increase the temperature of 1 kilogram of substance. So specific heat capacity, changing the temperature; latent heat, changing the state. And because there are two state changes, there are two different values for latent heat. So we're going to look at fusion first. So fusion, latent heat fusion, is the energy required of water. We're just looking at the energy required to melt 1 kilogram of water, i.e. ice, without a change in temperature, i.e. it's got to be at 0 degrees Celsius. Okay, so if you wanted to melt 1 kilogram of water when it was at 0 degrees Celsius, it would require 334 kilojoules for that kilogram. But we don't use kilojoules, we use joules, so it would take 334,000 joules to melt 1 kilogram of ice when that ice was at 0 degrees Celsius. Or if we like, we could think about it as the energy required to be removed from 1 kilogram of water at its freezing point at 0 degrees Celsius to then freeze it and turn it into ice. So we would need to remove that from ice at 0 degrees Celsius. Okay. So if we compare that to latent heat of vaporization, the latent heat of vaporization of water is all about water turning into vapor. So we're talking about boiling or condensing. And this is the energy required to vaporize 1 kilogram of water at its boiling point, which is 100 degrees Celsius. And that amount of energy is 2,260 kilojoules for every kilogram of water. Remember, we've got to get rid of that kilojoules. So it's 2,260,000 joules for every kilogram of water. So if you've got 1 kilogram of water boiling in a pan, you need to add this extra amount of energy to turn all of that boiling water into steam. This is not about heating it up to boiling point, that's specific heat capacity. It's about turning it into a gas or a vapor. Or if we like, we could think of it as the energy required to be removed from 1 kilogram of steam at 100 degrees Celsius and to turn it back into water. So we would have to remove that amount of energy. So remember we talked about steam burns. If the steam touched your skin would remove that amount of energy from the steam. Your skin, your body would absorb that amount of energy, and therefore you get burnt by the steam changing state. Okay, so we've got latent heat of fusion of water, that's 334,000 joules per kilogram, to melt 1 kilogram of ice. That's how much energy it would take. And if we had 1 kilogram of water at 100 degrees Celsius, it would require 2,260,000 joules to completely boil that off. Okay, so let's have a look at what this might look like as a graph, because we love graphs in physics. Let's say we're going to do a little experiment with some wax that we have in liquid form, and the starting temperature is going to be 80 degrees Celsius, and we're going to do this down to room temperature, which we're going to say is about 20 degrees Celsius. It's probably about 12 degrees Celsius in C6 right now though. So we're just going to, let's pretend we've done an experiment, we've heated up some wax, and we've got wax in this liquid form, and we've just left it in the room. And what's going to happen is that the temperature of that wax is going to decrease. It probably in reality wouldn't be linear like that, but I'm just going to simplify this for you. And it's going to decrease because obviously the room is at 20 degrees Celsius and the wax is at 80 degrees Celsius, so the wax is trying to get down to this room temperature. So this here would be the specific heat capacity equation that we would use to calculate any energy during that little change of temperature. But then at, let's say, around 50 degrees Celsius for wax, this happens. So during this stage here, it's solidifying. It's turning into a solid because there's no change in temperature. This is where we would use the latent heat equation. And then what would happen is it would just go down and it would reach room temperature again. Okay, so we could say then specific heat capacity equation because it's changing temperature. And of course, at room temperature, this doesn't mean it's changing state. What's happening there is it's in equilibrium, i.e. equilibrium, which means it's at room temperature. It's the same temperature it's surrounding, so why would it change state or anything there? Okay, so we've got cooling down. If it's cooling down, it's specific heat capacity we're dealing with, and then this is also called the freezing point. So 50 degrees Celsius equals the freezing point of wax in this graph. Okay, so this time let's look at what happens from if we had ice at 0 degrees Celsius. So if we're going to heat up ice at 0 degrees Celsius, that ice would stay at 0 degrees Celsius for a little while until we had water at 0 degrees Celsius. And this would be the latent heat of fusion. So we would need to add that amount of energy to, if it was 1 kilogram of water, it would be that 334,000 joules. But once all of that ice had turned into water at 0 degrees Celsius, then the temperature would increase. And again, I'm simplifying this. It probably wouldn't be a straight line. It would be more like a curve, but I'm just leaving it like this. And this is the specific heat capacity because we're changing the temperature of it. But once it gets to its boiling point, it doesn't go any higher than the boiling point. All of the energy that we're still adding into this water is then turning that water into steam. So this would be the latent heat of vaporization equation. Okay, and therefore this is the boiling point. So notice at the boiling point and the freezing point, the temperature doesn't change. So what we've got here then is water at 100 degrees Celsius, and in this point here we've got boiling taking place, and we're turning all of the water into steam during that. And here, in this point here, that's called melting. Okay. So let's do a couple of examples for you to follow. So here's the first one. We're going to start off quite basic here, in that it's a bit blurry. That should give you a sec. There we go. How much energy does it take to freeze 300 grams of water if the latent heat of fusion of water is 334 kilojoules per kilogram? So the equation for this is the energy, E, is mass times latent heat. We don't need to put the F or the V there, but I could do if I wanted to just say, right, I'm talking about fusion, so I'm just going to put LF there. We've got to make sure the units are correct. So 300 grams. So the mass for 300 grams has got to be in kilograms. So it's 0.3, and I'm going to just put the units there so that you can see that the units are consistent. And now I'm going to multiply that by the latent heat of fusion. You can see that we've got kilojoules here, and that's not the right unit. So the only time that kilo is the right unit is when we're talking about mass. Kilograms here is correct for all mass, and then everything else shouldn't have a kilo next to it, just the mass. So that should be 1,000 times bigger, so 334,000 joules for every kilogram. So you can see I've got kilograms and kilograms, so my answer is going to come out in joules here. So I'm just going to get my calculator. And I'm going to get 0.3 times 334, I'm going to use standard form here, times 10 to the 3, like that. And I don't like doing that, I'm going to use standard form. 100 times, sorry, 100.2 thousand, so it's going to be 100.2 kilojoules. I'm going to leave it like that. Or if you like, 100 that joules, or if you prefer, 100.2 times 10 to the 3 joules. So we've got 3 ways in which we can write down that amount of energy. So a second example then, a little bit harder. So we've got some water that's already at 100 degrees Celsius. So we're not talking about specific heat capacity. And we're going to add 565 kilojoules of energy, and that boils off some of this water that's at 100 degrees Celsius. And the question is, how much water does this 565 kilojoules turn into steam? So we're going to write down the equation first. So the equation is energy is mass times latent heat. It's the same as this equation up here. It's exactly the same, but we've got to use the different type of latent heat. This time it's vaporization. We don't need to put the lowercase v there. I'm just doing it to show you that it's the different type. And the latent heat of vaporization is 2,260 kilojoules per kilogram. And this is for water, okay? So we've got to make sure that the units are in the right place and everything like that. And we've got to make sure that the equation is in the right. So I'm actually trying to calculate M, because this here is E, and this equation here, or sorry, this variable here is latent heat. I'm trying to calculate M. So I'm going to rearrange this. M is going to be E over LV. Notice that the energy is in kilojoules, so I have to convert that into joules. So that's 565,000 joules. And I'm going to divide that by the latent heat of vaporization, which is going to be 2,260,000 joules per kilogram. I'm just going to put units there just to show you that my units are in the right place. So this means that my mass that comes out is going to be in kilograms, because this joule and this joule will end up cancelling each other out. So I'm going to get my calculator and to do this. 565 times 10 to the 3, that's 565,000 divided by 2,260 times 10 to the 3, and I get 0.25. So the mass is 0.25 don't forget the units. It's going to be in kilograms. So that amount of energy will boil off 250 grams or 0.25 kilograms of water when it's already boiling at 100 degrees Celsius. Okay, and the last example that you can work through with me is a little bit more complicated. So here we've got 75 grams of water that's at 20 degrees Celsius, so it's been in the room, and this person is then going to try and make ice out of it, and it's placed in a freezer. We want to know then how much energy is required to freeze the water, and this is the extra bit of information that we need, along with the specific heat capacity. So the specific heat capacity of water, C, is 4,200 joules per kilogram. Now we don't necessarily need to use all of this information, but because it's freezing, we need to do this, and because we're cooling the water down and changing its temperature, we need to do this. So we need to use two different equations to do that. So I'll break it down. Number one, we're going to cool the water down from 20 degrees Celsius to 0 degrees Celsius. That means we use the specific heat capacity equation, which is that. Okay. So the mass, we've got to convert 75 grams into kilograms. So that is 75 divided by 1,000, which is 0.075 kilograms. So 0.075 kilograms times the specific heat capacity of water, which is this value here, times 4,200, times the change in temperature. So it's at 20 degrees C, and we want to cool it down to its freezing temperature, freezing point, which is 0 degrees Celsius. Okay, put that into a calculator. 0.075 times 4,200, open my brackets, 20 minus 0, close my brackets, press the equal sign, 6,300. 6,300 joules required to cool the water from 20 degrees Celsius to freezing. Second thing then is to solidify the water at 0 degrees Celsius. And to do that, I need to use the equation E equals mL. So we'll look at which L is it. Is it fusion or vaporization? So it's the fusion one. The fusion one is responsible for solidifying or melting. So the mass is still the same, and the fusion value is 334, make sure the units are correct, 1,000. Right, and the calculator, 0.075 times 334 times 10 to the 3, that's 334,000, and we get 25,050 joules. I hate doing that, so I'm just going to press the ENG button here. Press that. I'm going to turn it into standard form. That's much nicer. Which is 25 times 10 to the 3 joules to 2 significant figures. So we've got our two energies there. This is the energy required to cool it down to 0, and then while it's at 0, this is the amount of energy then that's required to solidify it. So the total energy equals 6,300 joules, joules, plus the 25,050 joules. I'm just going to convert that into kilojoules. I'm going to say that's 31.35 kilojoules. Alright, I'll do it in proper language for you. 31,350 joules. And that's the total amount of energy that will be required to cool down water to 0 and then freeze it.